So if you hit in the TLB, life is good. You get the address you need. If you miss, there's two major approaches to figuring out where to go look for the data, or where to go look for the page tables. The approach that something like x86 uses is to use a hardware page table walker. So there's a little state machine in the main processor which says, oh, page table miss happened. It stalls the whole processor, and then what it does is it, in physical memory, will walk that multi-level page table for you. And we'll do index into it, and another index, and another index if it's a multi-level page table, and finally come up with the actual address. It'll refill the TLB. And this is like the miss case of your cache. Another common approach, which is what MIPS and Alpha do, is they'll actually use software to do that walk. And effectively what this is similar to having the miss case of your cache be done in software, or it's done in the operating system here. And why this can work out and not be too horrible is because TLB misses are relatively infrequent. So because the TLB miss is relatively infrequent, you can try to do it in software. Something I did want to say is that you can also, because it's being done in software, you can have different layouts of your page tables. You don't have to have one very rigid page table layout. Because if you do it in hardware, that means the layout of your page table has to be known between the hardware and the software, and they have to be agreed on. And that can cause challenges. Let's see, one other thing I wanted to say. PowerPC is actually a little bit interesting here. We have it put under hardware, but it, to some extent, can sort of straddle these two a little bit. Some implementations of PowerPC do this completely in hardware, and some actually have some software assist for the harder cases. And you could also think of the software ones sometimes having a little bit of hardware to assist. So for instance, in MIPS, there's a special hardware register that gets loaded with the address of the first level page table index if you're doing a multi-level page table. And the software can elect to use that register or not. So it's like a little bit of hardware boost, but it doesn't do the actual cycling of the page table in hardware. Instead, it's done in software. Just wanted to briefly show an example here of real page table structure. This is the Spark page table structure for their 32-bit Spark. They actually have 3 levels of page tables. Something to think about. You can have, and the memory management unit will do the walk in hardware. So it will index and then index into it again and index into it again based on these different indexes to come up with the physical page number if you have a TLB miss. OK, now we get to put it in the pipeline. So here's our 5-stage pipe. We want to be able to access our caches. And accessing our caches with virtual addresses could be problematic. We'll talk about that in a second. But it would be nice to be able to access them with physical addresses. So we want to go through our TLB to be able to access these caches. Well, all of a sudden, we've added something to our miss path, or excuse me, to our hit path, actually, of our cache. We put something in series with it. This can slow down our cache access. That's not great. I wanted to show something else being drawn here. Here's the hardware page table walker. So if you have a miss, it stalls the whole processor and fires up, and it'll actually use the page table base register to walk around in main memory and figure everything out. And usually, the page tables are held in untranslated physical memory. Because if you have to go through virtual memory to go touch your page tables, to go manage your page tables, it's a real big headache. But this makes life a little bit easier because the data cache and the instruction cache and the memory is all physical addresses. And we don't have to worry about any of this virtual memory stuff. OK, that's not so bad, except for I don't like how this slows down my processor. OK, so let's look at big, putting it all together here, perspective. You have a virtual address that comes in, goes through your TLB. If you get a hit, you check to make sure you can read it or write it, or you have access to it. If you do, you just access the cache, and life is great. If you don't, you trap into the operating system, and you with a protection violation or some sort of segmentation fault. Your TLB lookup here, let's say you take a miss, you end up with the page table walker. Now, this might be a hardware page table walker or a software page table walker. And this is where we start to see virtual memory showing up. So I said we would go back to memory on disk. Well, this is where it shows up. In the page table, the data could be in secondary storage. It could be on disk. And we can figure that out right at this point. And the operating system will be notified if it's not in the page table. So if the page table entry is invalid, you end up in the page fault handler. If it is valid, if you have a hardware page table walker, the hardware page table walker will update the TLB, and you go to re-execute the exact same instruction that you just faulted on. Or if you're a hardware page table walker, you're not even going to take a fault here on this path. It'll just stall the pipe for a bit. If you have a software page table walker, you'll actually have software doing this little part here. Now let's say the page exists, but is on disk. We somehow moved it out onto disk. Well, the page fault handler will actually load the page into memory, read it off a disk, patch the page table such that it now points at the correct place in memory, and then re-execute the same instruction, so return from interrupt at the instruction that took the original page fault. So this turns into, if we put this all together, we end up with our modern virtual memory system here. And our modern virtual memory system allows either memory to be in memory or memory to be on disk. And one of the cool ideas that people came up with is some fancier ways to manage this. So we end up with what's called demand paging. So in demand paging, we don't load anything when we start a program. If you go run a program on Linux, believe it or not, all it does is it maps in the first page of your executable and just starts you executing. It doesn't pull in the entire executable. If your executable is 5 megabytes, it pulls in 4 kilobytes worth of that on x86 and starts you going. And just you start executing. Now what happens is when you go to run, let's say you're executing, you execute off that 4 kilobytes, you end up in this page fault handler. Now the OS has a table. It might store it inside of the page table, or it might store it in a side structure. It knows, oh, well, the rest of that executable is still on disk. So it goes and it grabs that bits off disk and puts it into memory, maps the page, and restarts the load that missed, we'll say. And this works not only for portions of the executable that are on disk, but this can also work for things like your heap. So if you go to try to access off the end of your heap, and the OS knows that you actually allocated that space, it can just actually create new space for you and go find some page in memory for that space. So believe it or not, on a modern day x86 processor on running Linux, when you go to call malloc and you allocate a bunch of space, that space does not get created for you. Nothing happens. This is why malloc happens is really, really fast. The page does not get created until you first touch that page. So it's just smoke and mirrors in the meantime. And this is called demand paging. So during that first time when you call malloc, it just does nothing. The OS keeps track that, oh, it should have given you some memory, but it didn't. And then when you go to actually go touch the piece of memory that it was supposed to give you, at that point, it goes creates memory for you. And the reason it does this is because it decreases the memory pressure. You can actually run more programs if the programs are not executing the memory. So let's say you have a program which just allocates mallocs a lot of space, but then does not go to access it. Well, it didn't have to go allocate memory for you. This causes some challenges on the flip side, though, of all of a sudden, let's say you have 100 programs running, and they all alloc, I don't know, a gigabyte of space. They all call malloc of a gigabyte. The OS will just say yes, 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 yes to everybody. And then everyone goes and tries and access that gigabyte of space, but your machine only has, let's say, 4 gigabytes of memory. But all of a sudden, it promised 1,000 gigabytes of memory. Well, when that goes to, when your programs go to actually go access that 1,000 gigabytes or that terabyte of memory, which it doesn't actually have, at that point, one of them is going to crash, basically, and you're going to get an out-of-memory error. So this is the flip side of this demand paging scheme, is that your OS has to be very careful not to run out of memory, but sometimes it does. So we're going to let's stop here for today. And next time, we're going to finish up this lecture and move on to some other topics. But I just wanted to, I think we're running a little bit late today. But next time, we're going to talk about how to integrate translation look-aside buffers with caches and how to integrate them into the pipeline. So there's a lot of complexities in doing that. It's very possible that you don't want to actually access the TLB first before you go to access the cache. And we're going to talk about how to do that. I mean, the main reason you don't want to do that is it increases your time through here. OK, let's stop here for today.